Hi everyone, welcome to the session on this Greenplum 7.6 release that was released end of October. Today I am joined with my colleague Ashwin Agarwal, who's the tech lead for Greenplum, and we are going to focus our attention today on the storage enhancements that came in the recent release for Greenplum 7.6. As mentioned in the other video, we have five dimensions in which we are always trying to innovate and keep up with the latest requirements and the next generation Greenplum 7. One of them is storage and replication, how we can better support our ever expanding requirements on storage and replication solutions, making the queries faster, enabling people to ingest and cache data when they have different ETL, ELT operations, how you can ingest it, how you can cache it, how to perform AI, ML, spatial, vector searches, text analytics, all of the analytical features that are needed by our customers. And lastly, how you manage the Greenplum clusters, how you monitor them, and how you can provision all of your resources. So those are the five dimensions. And today we're going to be focusing on the storage and replication part, more specifically on storage, and that's what Ashwin is here for to focus on. So take it away, Ashwin.
Okay, thank you, Venki. So, extremely happy to present what we are delivering in the space of storage and replication as part of 7.6 release. The first part, which is pretty game changing technology to enhance our columnar tables in Greenplum, is the feature which we are calling implied indexes. So, just to give a brief background of what this feature brings in, is it changes the way very natively how columnar scans are going to work. And the best part about the feature essentially is that it's not like something you have to opt into or do some tweaks around. It would be a feature once you upgrade to 7.6 release, gets enabled, and improves the query performance for columnar table, for sequential scans, and for index scans. The main aspect or the theme around the feature is to explore how the columnar design is and how that columnar design internally the storage layout is can be used to avoid creating or requiring to create an external indexes. Instead, how we can leverage the storage format to natively apply indexing technology to it. What that allows you to do is essentially helps you to have like much better query conditions and like only select rows or perform IO for the rows which are really required in the system. And the other biggest benefit for this implied index, which regular indexes don't allow, is even for filters which are across multiple columns, it can still leverage the indexing method, which native B-tree indexes, gist or gin indexes don't do. So let's dive in and see what we are bringing to the table. To first bring all of us on the same page, I will just go through what exists in the current state of the world. So, for regular columnar table in Greenplum, when you have this kind of query, which is like select from where some column has a filter condition on it, we currently, if you don't have any indexes, you don't have anything else, we have to scan like each and every column in the table and then apply the filtering condition and return rows. So it essentially is like scanning all the columns. And then it is stitching all these columns together. So it has to stitch and form a row. So it has to scan column 1, column 2, column 3, stitch together, apply the filtering logic, and then return the tuples above. That's what the current state of the art is, what exists without implied indexes in the system. If you are not having any kind of indexes, and if you have to execute this query, it entails to scanning full table with all the columns, CPU cost of stitching and processing all the columns, and then the filtering applies for this column which you have specified in the filter condition. In case you are creating indexes, definitely that aspect gets improved compared to like doing a sequential scan of all the columns. The column on which you at least have the index defined. So in this case, if you have an index defined on event type column, then we would be doing an index lookup. So we would go through, let's say you have a B tree index, it will go through the B tree index pages, figure out the tuples which match whatever the conditions you have, and the index can give us exact row IDs of which tuples map. So taking those row IDs, then we would actually fetch only those specific rows from the actual table. So if you have an index on a columnar table right now, an external index, it definitely helps out to speed up that we are avoiding doing the full table scans. Index is giving us the actual rows to go and fetch. Though this still comes with a cost, it's not a thing which comes for free. Now, what are the drawbacks? So, the drawbacks of having an external index, first one is in this case, given you created an index on the event type column. Now, if you are doing a where condition which is not on the indexed column, let's say it's on the severity, it's on location. Now, you cannot be creating index on every column in a database. So if any of the filters are on the columns which don't have index, then it falls back to doing the full sequential scans. So that's one of the problems where you can only be creating index on a finite set of columns. But if you have ad hoc queries, indexes and indexing method falls apart. The second is indexes come with their own cost. The biggest one is space, because index at least columnar tables AOCO have compression enabled, so the data which lands on the columnar table at least gets compressed, but the indexes are not compressed, and it's a BT data structure. So when indexes are existing on a columnar table, they definitely end up eating up space. Plus, any indexing comes with the cost of maintaining the index, because when you are loading the data, we have to load and maintain the indexes. When you're doing updates and deletes, we have to perform those operations on the index. Also, regular vacuuming on the table, you have to regularly vacuum or re-index the index as well. So all this, like having a separate index from the table, comes with its own cost. It's not, doesn't come for free. And the last thing we mentioned is it doesn't support multi-column indexes. So if you have like where clause with like two columns in filter condition, then again index is not going to help you out. We can only do external indexes, help you mostly for like single column things. So how do we improve the state from what we had discussed before? Like these were what the current behaviors were. So to improve on the current state, we came up with implied indexes as part of 7.6 feature. Now the biggest theme which it exploits is that given columnar table, the layout is each column has its own file. So you can actually go and read just column 1 data independent of any other columns in the system. So this is the biggest property which we are exploiting as part of implied indexes to perform the qualifications from the table itself. So you don't need to create a separate index on the table. We would be using the columnar table storage format itself to act as indexes. And that was the reason the name is given implied index. So the way this thing works is, let's say given a query, you have select star from T, where like the column on which you have the filter is C2 and you are interested in value equal to 2. In traditional time, we would have like selected full table and done the qualification after we have selected all the and scanned everything in the executor. With the newer feature, what we are doing is, given the filter condition is only on column 2, C2, we first go and scan only C2 as the column. Start scanning the column, and only the rows for which the filter condition is met, With the help of block directory, we are going to read rest of the column data. Let's say C1 and all other column data will be read only for the rows which match this filter condition. So with this, it's very intuitive enough to see like how much IO saving happens, because we are completely excluding to read any of the blocks which fall and don't meet this condition of C2 equal to 2. So in that sense, C2 is acting as index from the table itself without any external index creation. The main aspect on which this concept works is essentially block directory, because block directory is the data structure which allows us to do this mapping from like given a row ID where that row falls for all other columns. So for AO and CO tables today, if you just create AO and CO tables and you don't create an index, block directory is not created for that table. Now, for this feature to work, having block directory is the part which adds efficiency to the system. So the only thing required is essentially don't create any indexes, but at least create block directory for CO tables. And having the block directory will make the system use implied indexes for those tables. For that purpose, we have introduced two syntaxes which are enhanced. Like during create table time, you can say for columnar tables to force creating block directory when the table is getting created itself. Or for the tables which are existing in the system, so you have existing columnar tables and you want to leverage the implied index feature, you can just do alter table set block directory, which will just create block directory. From that point forward, it will maintain the block directory for the CO table. So just having this block directory effectively helps us to optimize the process. And there is a plan for next release to make this flexibility that even without block directory, implied index will be able to leverage the feature. It will be still not as optimal as with the presence of block directory. But for 7.6 release, block directory is a must to work for implied indexes. Now, to zoom into how implied index is actually saving or making it performant compared to like normal sequential scan. So the biggest thing implied index is doing is it's allowing us to skip IO for the blocks which do not contain the result rows. And it is helping us to do the CPU optimization, because you're not even reading those rows. We are not even processing those rows. So the disk IO, uncompression, CPU processing time, all those cut down with the help of implied index. What gets added though is the metadata lookup, because if you have to do the skipping, we are avoiding to read the actual data, but there is small amount of metadata which we have to read to perform that skipping operations. That's what block directory gives. So it comes with little cost added of reading block directory and doing processing for the block directory IO. So the code, both Orca and Planner, has been enhanced to perform a cost-based decision of making the cost analysis of how much we are adding to the cost and how much we are removing the cost if a query comes in, based on the table size, based on what the filtering conditions are, all that. And Planner and Orca are going to make cost-based decision of should they opt in to use implied indexes or should they fall back to normal doing sequential scan and all. So these are all the attributes which the planner and Orca are going to use to make that cost based decision. So switching gears and moving on, what effectively we will be going through like some of the performance numbers, what allows us the feature and like showcases where the benefits come from the feature. To understand that theme of what the performance numbers and like experiments we focused on, the two attributes which focuses on are selectivity, like how many rows are actually getting selected for a given query, because that is one thing which affects how effective this implied index becomes versus like how equal to sequential scan the results would be. And the other aspect is, given it's a columnar table, the target list also matters of how many columns you're actually selecting out of the column, full table. If it is a 500 column table, are you selecting one column from it, or are you selecting like 100 columns from it? Will also make a difference in terms of how or where you will see the gain in terms of implied indexes. So the first result we are going to go through is figuring out, like just giving the raw numbers based on highest selectivity to like much lower selectivity, where like 50% of the tuples are being read on the table, what query performance generally implied indexes give. So if it is like a very, very highly selective queries, then you can see, compared to like sequential scans, implied indexes is actually much, much, much beneficial, because it's going to scan only one column. You will have like only one or two rows being returned from it. So we are going to do IO only for rest of the columns for those one or two tuples. So that's where it really shines, where implied indexes, the column, the queries are highly selective. But even in cases where the query is not very highly selective, it's still performant compared to the regular sequential scans. Just the performance gain will vary based on the selectivity.
So, question, Ashwin, how does being super selective makes very sense, but where do we get the performance benefit when it's lesser selective?
So even if it is less selective, so in this case, even if we are like only 50% of rows are returned, still for rest of the 50%, we are avoiding to read rest of the full table. Because otherwise, like if we just do sequential scan, we are reading 100% of all the tuples and then stitching together. So stitching together column data like column 1, column 2, column 3 and form a full row is still a costly operation, which gets avoided. So even if we are able to avoid it for like let's say 20-30% of the rows, it offsets out the cost of reading block directory, and still implied indexes become faster
Okay.
for the case. But like in cases of 100%, like nothing is getting opted out and all the rows have to be returned, I think for those cases, first either optimizer or planner is not even going to pick the implied index, because the cost for implied index is going to come out much heavier than the sequential scans.
Okay.
But even if via plan hints or guck we force the behavior, you would definitely see that because of the additional block directory cost, it adds up and then implied index would be actually slower.
Oh, by the way, Ashwin, you gave away the next release. The feature that is coming out is optimizer hints. You
Yeah.
kind of sneaked it in, but yeah, in the next release, or you can users can add in the SQL itself to pick implied index on scenarios that they want to force the optimizer to pick it. But yeah, that's a sneaky introduction of roadmap. Okay, go ahead.
Okay, perfect. Then moving on, the other attribute which helps how much query performance you would see from the feature is how many rows you are selecting. So like if you are selecting too many, like lot of rows from the table, then definitely the impact or the gain would be higher, because if you're selecting like 20 columns from the table, you're eliminating reading data compared for all those like 20 columns. So in those cases the benefit seen would be much higher. But if you were selecting only like few columns, given already you were selecting less data, the impact seen from the implied indexes would be lower. But that's the beauty of the feature. All of this is done by the planner and optimizer internally to figure out when it would be useful and when should use implied index and when should not. So that takes away much of the burden from the users to.
Is there, I have a question here. Does this seems like with implied index, it's the cost is constant, kind of constant-ish.
Correct. Yeah, because the reason for cost being constant is irrespective of how many columns we were selecting, the IO rate remains the same because we are not reading unwanted data. So with implied index, you are only reading the data which is always consistent and wanted. So it doesn't matter you select like 20 columns or you select one column, all of these are going to read the same amount of IO on
So
the
your
disk.
projection does not matter. Your projection does not matter, correct? Okay,
Yeah.
got it.
And that's the reason the performance is very consistent with even if you are reading one column or more columns because the indexing is helping you eliminate a lot of noise. The other attributes which help also are like what kind of calls you have. If you have like or you are using and how many columns are there in the where clause, because depending on number of columns in the filter condition, that many columns we would be reading first to do the qual checking, and then we would be doing whatever is in there your target list. So if the number of columns in the quals are too many, it might end up reading like the whole table is required to be read, then the effectiveness kind of goes down. And the selectivity definitely plays a role in this case also. So here the graph which you have, like if you have only like one column you have in the qual, in the where clause, effects are much pronounced because we are only reading one column and then doing the qual check, which because of high selectivity is excluding to read all other columns. But if like let's say you have a where clause which has like 16 columns in it, then like we have to go and read at least those all those 16 columns to perform the qual check. And because of the number of columns increasing in the qual, that many column data has to be read, the performance will not be that much pronounced compared to the less number of columns in the where clause. So
It
that's
is
the
kind
other
of
attribute.
unrealistic to have 16 qualifiers, right?
Correct.
Maybe it's a
Correct.
general use case is users have 4 to 5 you calls. That's a general typical use case, correct? If you
Right.
have 16 calls, then maybe we need to do some data re-architecturing.
I 100% agree. So we just wanted to showcase like extreme ends to see where the bandwidth is, and those are the attributes also which are taken care in the
It's
costing.
quite impressive, even for 8 or predicates. It's quite, you get significant performance improvement. Yeah.
Yeah, 100%. And then the last one goes into like and instead of or you have and conditions. So and definitely allows you to actually like quickly prune and filter and stop reading more columns, even if there are like lot more columns in the qual, because you can do the pipelining where like the first one doesn't qualify, then we will actually skip reading the next column also. So that way, with even 16 columns, you see like there's still huge benefit with which exists, which is generally not the case which happens for the regular stuff.
So I think the difference between the and the or is because and is more filtering, incrementally filtering. So even if you do more, you will still get good benefit.
Correct.
While an or, it's less so. Got it.
Less. Yep. And if you do the comparison with the B-tree index, B-tree indexes are still definitely better for the point queries. Implied indexes is not really like complete replacement for all type of queries. If it's like very point query, B-tree indexes can give you much better performance because with implied index still the column one has to be fully read. Compared to that, B-tree can actually give you the point only through that one page, and then we can read and return the results from. So because of that, for B-tree indexes, if exist on the column, implied index will not get picked, and that's the reason this row there's no change with the feature. But if you have like where clause which has two columns involved, in that case now B-tree doesn't even work. So for those cases, implied index actually gives you huge benefits. Same is here. Like if you have anytime you have like columns on which you are doing either computation or you have like multiple columns involved for the table, B-tree index, even if exists on column 1, will not get picked, and we will be actually using implied index. And for those cases, the gains are much heavy and pronounced.
Can you just insight of how even when you do operations on a column, how do you how does this help? Because you compute
So
the value and then scan the one column, and that's why it the benefit, right? Is that what you're saying?
correct, yes. Because only like this column will get read, we'll do the computation on the and perform the qual check there itself. Then we'll actually figure out what all other columns
Got
have
it.
to be read. But B tree cannot do that thing, and that's the reason it doesn't work out for B trees. Okay, so the next set of feature which we will look at, which is part of 7.6, it's on the same theme of improving the columnar columnar scans for CO tables. What we are doing is we added optimizations in the very hot path, which is the visibility checking. For every tuple in the AOCO table, we have to perform if the tuple is visible or not visible for maintaining the MVCC characteristics of the queries. Now, the optimization effectively is to, again, similar way, exploit columnar conditions and perform the visibility check for a first column, whichever is being read. And based on that, then decide how much we can eliminate the IO for rest of the columns. So in this case, let's say we have the way the picture is, you have like rows 1 to 100 visible, and then you have like rows 1 to 200 which are deleted. Now in this case, if you are performing the visibility check, we can read the column 1, we can read all 100 rows, we know those are visible. For those, we'll read all the columns. But for the rows 101 to 200, given just when we are read column 1, we know that all the rows corresponding to 101 to 200 are in deleted set. We actually will not go and visit any of the rest of the columns to read the data from. We'll completely skip and move forward to read only data from 201. So any tables which have like heavy update and delete or are not performing regularly vacuum operations, very heavily this helps to eliminate the IO which is done, the decompression which is required for the columnar tables, and improve the speed of the scans. Plus, previously we used to perform the visibility check for every column independently. So that's the other optimization which happened, that even if you don't have anything deleted, all the rows are in visible set, but the visibility check is only performed once per row, not per column. So even in cases where the tables were not having like heavy bloat or are not having regular update and delete operations, still the optimization would help to increase the performance for sequential scans, and same will happen for both index scans. So that helps out. The last optimization in the same bucket is if you have performed add column operation on the table. So as part of add column optimization, when you're adding a column, we actually don't write all those rows to the table. The default value for the added column is only stored in one place as metadata. So this full file is kind of like partial or incomplete file where the data is in metadata and we can serve the queries just based on metadata. So for any kind of tables which have gone through these add column operations, for the columns which are added, those kind of become like partial files on disk. And for those tables also, the optimization kicks in where we don't have to actually go and read the block directory and perform visibility checks. We already know that we can serve it from the metadata. So that also gets optimized. So the tables gone through add column will see also the optimization and performance benefit from these enhancements about visibility checking. So the results just depict how, in which kind of scenarios, the benefits are much more seen. And given the maximum optimization comes in where we are skipping reading rest of the columns, if we determine certain rows are deleted or invisible, that is the reason if the table has like lot more tuples invisible, which is like a definitely the extreme case, like 90% tuples are all deleted tuples, then the gain is pretty huge because we are eliminating reading any of those tuples actual data files. The other factor which matters and which will differ in which how much gain you get from these optimization is how contiguous those performed updates or deletes are. So this 90% is like intermittent, which is like, let's say, spread across the table. Then the gain is like around 21%. But let's say these 90% tuples are all contiguous, like either front of the table, in middle of the table, or at the end, like they are contiguously all dead tuples together, then we can actually skip out blocks and blocks of data in those cases. And if the table is actually compressed, then for sure much more benefit is seen because you save on the IO and you save on the CPU cost of decompression. So for those kind of like very extreme cases, there's like huge benefit, somewhere around even 70% gains you can see from these performance improvements for the optimization. And similar result will be seen for what we had seen in previous slide was for sequential scans. Index scans, the same concept gets applied, and then the benefits are in similar buckets of like how many rows a table has. You will see varying benefits, but the optimization definitely is helping, and it's in the same theme as like you don't have to opt in into the feature. Once you upgrade to 7.6, these optimizations will get applied to the index scans and sequential scans for your database. The last one, this slide presents the optimization numbers for the add column operation. As I was saying, like if you had like 8 columns in the table which were added, so that's the what we call like 8 partial columns, because for those eight columns you added, the metadata is stored in the catalog and actual data is not even present in the file. So the more number of columns you have added to the table, the optimization would be higher for those kind of tables. So if your workload goes through like a lot of add column operations for CO table, this optimization would be actually much more seen in your workloads. Moving on to switch gears little bit from just columnar table optimizations to this bucket of improvements which we have for 7.6 is little more across the board for storage. So they get applied for normal like heap, AO, row oriented, column oriented, like much broader bandwidth of the workloads. What this feature brings in is we are leveraging one of the hardware instructions, which allows you to do like vectorized CRC calculation. Now, within Greenplum database, we use CRC for doing data protection for many of the areas. So all the wall which gets read and written have checksums for them. All the append optimized row tables, columnar tables do checksumming for every data block which we write. Now, writing into external error tables, when you're loading data, whatever error table data gets written, they are checksummed. And there are more places where database does checksumming inside. So for all those checksumming operations, now if you are on a newer hardware which supports these kind of SIMD instructions as you're on the platform, then you will see actually huge gains from the vectorized execution because Greenplum code has been enhanced to check on runtime that if these instructions are available on the platform, and if these instructions are available, instead of doing the normal CRC calculations, it would use these CPU-centric instructions to perform the vectorized CRC. In some of the experiments which we have done, we have seen like almost like close to 50% improvements for doing these CRC calculations, because it's using the hardware instruction set to perform, and the data sizes on which it does these are much bigger than like just doing it like smaller granularity. So for the workloads which are much more, let's say, CPU intensive, not very IO intensive, like kind of queries where you're just doing a select star or select count star on a table, which was reading all the table but not doing much CPU processing. For that, this, because of the checksumming during read becomes so fast, it can be seen as like 40% improvements are what we have seen in our experiments when we ran on platforms which supported all these vectorized instructions for CRC calculations. Similar in nature is along with the CRC to speed up with these instructions. Lot of times we have to operate on like bitmaps in green database for performing like visibility checks for heap tables, for append optimized tables. There are a lot of like planning and executor nodes which perform bitmap operations, and now we, even to perform those bitmap operations for doing, we leverage, if the platform supports, the AVX instructions. And using that, again, because it's hardware optimized instructions and vectorized execution, which we are doing for these bit counting on bitmaps, you can see pretty much huge gains if that portion of the query is more where the time is spent. So in some of the synthetic benchmarks, which were like having operations very selectively doing a lot more bitmap operations, 25%, 18% kind of gains is what we have seen by moving to usage of the vectorized instructions in the system. Yeah, so that was mostly what we had delivered from the storage footprint for the 7.6 release. What
Thank
do you
you.
want to say, Venki?
Thank you, Ashwin, for joining this session. It is very informative. And I'm hoping that people upgrade to 7.6, give us feedback, what worked, and what additional features we can bring in. We are looking forward to hearing from you. And we will also have another session on query processing, as well as a session on cluster monitoring and management for 7.6. Please do watch those videos too. And the next release is 7.7 coming later this year. Thank you so much, Ashwin.
Okay, thank you.